Welcome to part 1 on logarithms and graphs. In this section, we're going to look at logarithmic functions and their graphs, and also compare common logarithms with natural logarithms and talk about how they're different. Let's first look at logarithmic functions and their graphs. And we'll start with a question. Are exponential functions one-to-one? And if I were to sketch an exponential growth function, it would look something like this. It increases as you go from left to right. And if we were to check if it passes the horizontal line test, we would say yes, this function is one-to-one. If a function, an exponential function, is one-to-one, we could say that the inverse is the graph of the line or the curve that is the reflection about the line y equals x. And if I were to sketch that, it would look something like this, where every xy coordinate is now yx values on this blue line. And even though the logarithmic function increases as it moves from left to right, it doesn't have a horizontal asymptote anymore. It now has a vertical asymptote at x equals 0. It does not cross the vertical axis. Now, transformations can shift this blue curve, logarithmic curve, left or right, but that shift will also imply that the vertical asymptote has shifted as well. So let's look at the definition. The logarithmic function with base a is noted by f of x equals log base a of x. You would read this as log base a of x. And it's very important to use this wording when you're talking about it instead of just saying log ax, because that will not make any sense to someone who is well versed in logarithms. And so as you become more well versed in logarithms, I want you to sound like you know what you're talking about. Now, this log base a of x has to have an a greater than 0, so you can't have negative bases. And a cannot equal 1, because as you will learn, that won't make any sense either. And x is a real number greater than 0 as well. So you cannot put a negative value into your function, your logarithmic function. So this x must be greater than 0. And lastly, this seems like a lot of rules, but I'm just giving you a lot of information all at once. If you were to graph log base a of x, it would have this curve here that I've already sketched. It appears to be approaching the vertical axis, the y-axis, as x approaches 0 from the right. And you would say as x approaches 0 from the right, y approaches negative infinity, because it's going downwards as it gets closer and closer to this vertical axis. That being said, if I wanted to rewrite my logarithm as an exponential, I can do that with something I like to call the log scorpion. You can take the base, raise it to the number or value on the other side of the equal sign, and then say it's equal to of x. So I could rewrite a raised to the y equals x. So I would say a raised to y equals x. I just want to emphasize that if you were to graph a raised to the y equals x, it would graph right over the top of your other function. So they are equivalent statements. And if you wanted to graph the inverse, would be the exponential, and it would go up and to the right. It would look like exponential growth. These all will be helpful pieces of information as you move forward, but let's solve some equations, logarithmic equations here, now that we know that we can interchange between exponential and logarithmic form. Because honestly, a logarithm is only helpful if you're trying to undo an exponent. Otherwise, it's very difficult to do those calculations as a logarithmic equation. So we will convert it to exponential form. So if I do that for this first example, I have log base 2 of 32 equals x. I'll take 2, raise it to the x power, equaling 32. So rewriting that, I will have 2 raised to the x equals 32. Well, I happen to know by the rules of exponents that if I can get my bases to match, I can drop the bases and just equate the exponents. So I have 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. This is equivalent to 2 to the 5th, which means if I equate my exponents, I will have x equals 5. And if you're trying to make sense of all of this as one thing, this log base 2 of 32 equals x is asking what number would I have to raise 2 to get 32 as my output. So that's where the x and the 5 come in. I would have to raise 2 to the 5th to get 32. Now for log base 3 of 27 equals x, I could say 3 raised to the x equals 27. If I rewrite 27, I would have 3 times 3 times 3, which is equal to 3 to the 3rd. Therefore, if I equate my exponents, I will have x equals 3. Let's look at these last 3 or 4 examples here. So I have 4 raised to the 1/2 equals x. Therefore, I would have the square root of 4 equals x, because a fractional exponent is a square root with index 2. X has to be greater than 0. That's a rule we already talked about. So that means that x can only equal 2. If I have x raised to the -2 equals 1 over 100, I need to figure out now what x equals, because my base is now the unknown. So now we're switching which part of the logarithm is unknown. So I'll take x and raise it to the -2, where I know by the rules of fractions and exponents, 100 if I were to bring that denominator, I'd have to have 100 to the -1. I also know that 100 is equal to 10 times 10, still raised to the -1, which means I could rewrite this as 10 to the 2 raised to the -1, which is 10 to the -2. That's a long process, but I just want you to see how you would go from a fraction with the interesting number in the denominator all the way up to what we have here. So since x to the negative 2 is equal to 10 to the negative 2, I can say, therefore, the three dots, x equals 10. Because I've made my exponents match, therefore the x has to be 10. Now let's look at 3 raised to the 0 equals x. Well, 3 to the power of 0 is just 1. So we have 1 equals x. That was pretty easy. And the last one here we have is x raised to the 1 equals 2. Well, anything to the 1 power is just that thing, so x equals 2.